All right. Hello, everyone. My name is Togan, and I am a member of the Entangled Nets team. We are going to present our project idea within the scope of QHack 2021, organized by Xanadu. Our project is titled Event Classification with Layerwise Learning for Data Reuploading Classifier in High Energy Physics. Initially, we had this idea. We wanted to solve a real-life problem. We checked a data set given at CERN. So, as we know, the large experiments concluded in the in the field of particle physics produce a large amount of data after the collisions, such as the experiments done in the LHC. These huge amounts of data have motivated the usage of machine learning, classical machine learning techniques in different aspects to improve the performance and the analysis of these data. Now, accordingly, the methods of quantum computing has been using in the last decades or so to help provide more improved analysis of these data. Now, furthermore, since the development of quantum hardware with sufficient number of qubits is still in progress, we think that we can use a method that will use the power of the computational power of single qubits. Now, therefore, we use the method of data reuploading. And the way it works, as we all know, a quantum state is represented is characterized as two-dimensional state vector and can be visualized as one point in the Bloch sphere. In order to load the data onto a single qubit, we use unitary operations. Now, let's say we start with the state 0 and we want to modify the state of the qubit on the Bloch sphere. We apply a unitary operation with the specific parameters these parameters will be as a parametrized matrix multiplication, representing the rotation of the state vector in the Bloch sphere. So, for example, if we start with the state 0 and apply specific unitary operation with different parameters, we will end up at a different point in the Bloch sphere. And applying more than one unitary operation will modify the state of the qubit this way. So we want, of course, this cannot be only used for one single qubit, but then for multiple qubits. And this is what we try to use to use this variation quantum circuit as a classifier, as a universal classifier, universal quantum classifier, to classify the data we obtained from the data set called SUSY. All right. Besides the reuploading technique, we have also modified version of used the modified version of Layerwise learning approach for parametrized quantum circuits, where individual components of the circuits are trained one by one, inspired by the reference article number 8, where only subset of parameters are uploaded in each training step. This strategy can help us avoid the problem of barren plateaus of error surface due to the low depth of the circuits. A lower number of parameters trained in one step and a larger magnitude of gradients compared to the training of the full circuit as described in Article 8 as well. Of course, this approach also makes the model preferable for execution on a noisy intermediate scale quantum devices, similar to the reuploading data technique. Okay, now I will pass it to Andre to explain us the circuit and the data visualization in depth.
Hi, I am Andre, and I will present the data that we have, more precisely the SUSY dataset that is free and available. So what we want to do, we want to find if our collision results in a desired particle or not. For this, we can't measure direct the particle because he has a short time span, but we can measure the decay products. And how we measure things, so we put some sensor and we identify some parameters. For example, the momentum of the point in some spot, and we can identify the direction. But in SUSY dataset, these data are not taken from a real device, are simulated using Monte Carlo. And here I have some graphs, some histograms with the distribution of the background signal and the signal that comes from a successful collision. From these 80 parameters, just 8 are first parameter and the second 10 are generated from the first 8. The most important parameters, as we can read in the paper that inspired us, are the momentum of the lepton 1 and lepton 2, and the difference in and the missing energy. These are the three basic parameters, but we also make tests with more parameters. And if we look in these graphs, we have a representation of the data, original data, in the right part of the screen. When we have this momentum of on the axis and missing energy on the z-axis. We also try to apply PCA, but we don't get a lot better results using PCA. The other parameters that first parameter are polar respective azimuthal angle. And sometimes we use eta instead of polar angle. And measuring the difference in potential from the particle that are registered by our sensor, we can calculate the missing energy that appear from the particle that are generated and we cannot observe them. Okay, now I will let Edu to explain the code.
Thank you, Andre, for the explanation for the datasets. So in our implementations, we only use a small number of subsets from the whole datasets. This is because we have little time and small resources. So we choose to use just 5,000 samples for both the training set and testing set. And we don't use the whole 5 million of samples because it will take a lot of resources and time. And we feel that 5,000 is quite a good number, considering the reference paper number 2 also only use a subset of the dataset up to 10,000 samples. Since we use the Penny Lane's rod gate or the rotation gate for the DRC, it is nice if we use if the total number of features we use is the multiple of 3. But we realize that in the future works, we also need to analyze what features is more important and how the number of features impact the training accuracy. Okay, and in our implementation, we decide to use the top 6 best features that is proposed by the reference paper number 2. The top 6 of the features based on the reference number 2 is lepton 1 PT, lepton 2 PT, missing energy magnitude, MTR2, M delta R, and lepton 1 eta. Those 6 features are the one that we use for this implementation. Next, this is the circuit schematic that we use for the DRC scheme. So we use the many lanes rotation gates, which receive up to 3 parameters. And because we use 6 features, so for every samples, we need 2 set of gates, because every gate will receive 3 features. And then this is the equation on how we embed the data into the parameters theta, and then embed the theta into the gate. So we can see in this equation, the W and B here is the weight and bias parameters that will be optimized during the training. And the variable X here is the value of the data sample, and the index M here shows the index for features, and L here is the index for layer. So this block of circuit can be repeated for several times. In this schematic, we showed that the block is repeated for L number of layers, and in our implementation, we set L equal to 5. And then the cost function that we want to minimize is inspired from the original paper of DRC. So in the original paper, the authors proposed the weighted fidelity cost function, which is this equation here. So we can see that the qubit, we only need 1 qubit, but we have to measure that qubit 2 times. The first one is using the 0,0 observable, and the second one is using 1,1 observable. And then we train the circuit by using the modified version of Layerwise learning, where we train each parameters from each layer one by one. So when we train the first layer, we make the parameters in the other layers, in the second and the third, etc., to be fixed. And then after the first layer is finished, we train the second layer and we freeze the other parameters. We repeat the process until we train all the layers. And then the difference is we do the last training, which train all the parameters in all layers. After the training is finished, we test the performance of our model. This is the best parameters that we get from the training. And from the testing results, we get the AUC score, or area under the ROC curve, about 0.85 for the training set and 0.848 for the testing set. This number is a bit higher than if we compare the results that the reference paper number 2 gets. And then we also use that optimized parameter and try to do the testing on real hardware. We use the Rigetti Aspen 9 QPU provided by AWS. Since the QPU device didn't support the 00 or 11 custom Hermitian gate, we use the Pauli Z gate for the measurement, and we can use this equation to get the same results as if we use the 11 gate, 11 observables gate. And to make the costs become more efficient, we execute the circuit for 10 qubits. So even though we actually only need 1 qubit for every samples, we use 10 qubits. So for every pass, we can get the results for 10 samples. This way, we can save the cost of our S device a lot. In total, we do 100 times of execution, both for the data samples with label 0 and with label 1. So in total, we did testing with 2,000 samples. And we use 10,000 shots in every circuit execution to get good precision. After everything is finished, we check the AUC score, and we got 0.8297, which is not so different with the one that we get from the simulators. And this result is also still better if we compared it to the one from the reference paper number 2 that they got with the real QPU device. In conclusion, in this project, we managed to build an algorithm and to train the quantum circuits to classify the SUSY dataset. We train it by using the modification of the Layerwise learning with data-reuploading classifier scheme. With just using in total 2 qubits for the training, we obtain AUC of 0.848 on testing dataset with 5,000 training and testing samples in a simulator. And we get AUC about 0.82 with 2,000 samples in Rigetti's real QPU device. Comparing this result, we may conclude that we were able to obtain a better results compared to the one in the reference paper number 2. And also the AUC obtained from the simulators are very close compared to the one we obtained from the QPU device.
I am grateful for the opportunity to take part in this hackathon organized by Sanadu. And I am happy that I was able to meet new people from different countries with totally messy time zone. And we were still able to communicate and work together as a team. I am very grateful to Togan and to Edu for their patience with me. And I am glad that we managed to run our circuits on a real device, on a real great device. And it was amazing to be able to work on the real problem. It was my first hackathon. It was amazing. Just thank you for your time and effort and feedback.
Yes, I also agree with what Andre says. We have a great time. We have some stressful times, but it was really great, and we managed to get this project done. Yeah, I want to say thank you to the Xanadu team for giving us this great opportunity.